continue with our discussion on equilibrium. Except now we're going to be using equilibrium to now study acids and bases, right? So there's a couple different ways we can define an acid or base. Generally, we know them as something that's very reactive once they get into solution, right? So that's why whenever we're dealing with acid base in lab, we have to be pretty careful on how we deal with them. So what are some common acids? Hydrochloric acid, sulfuric acid. We see those a lot, especially nitric acid also in the lab. Those are strong acids. We'll talk exactly what those mean. And then we have some of the larger molecule acids like carbonic acid and citric acid as well, right? So what these have a lot of the time is these acids have a structure where you have a hydrogen that's bonded to some sort of oxygen, and we call that an acidic proton usually, right? So acids, we usually refer to donating or dissociating protons, because usually in one of these acidic structures, it's the hydrogen that's bonded to these oxygens that are being dissociated to form what makes a solution acidic or what makes a solution basic. It's the movement of this protons, right? So the movement, the movement of protons goes hand in hand with acidity and basicity. And basicity. And in these structures, all the ones that I'm highlighting in red, these are considered acidic protons. Right, this is for acids. For bases, usually we do the opposite. We're going to be pulling protons rather than donating protons. Right, so the reason that these protons tend to be acidic is because of something you guys may have seen in first semester chemistry. It depends on who your professor was. Has anyone heard of resonance before? Well, once you get rid of one of these protons, right? So if we look at here, this is acetic acid, which is a common one. Does anyone know what acetic acid is? Acetic acid is very vinegary. Acetic acid is vinegar. That's the acid that's in vinegar. And so acetic acid, when we get rid of the proton, right, this is usually going to be donated to some water molecule, and we'll go through this process in detail. We're left with a structure that looks something like this. C double bond O. CH3, something like this. And so the reason that this proton is the acidic ones instead of the ones surrounding the carbon atoms there in the Lewis structure is because this negative charge is on an oxygen, which is a lot happier than a carbon having a negative charge. And because we have this double bonded carbon here, what happens is we get something called resonance that will stabilize this structure. I mean, this double bond is basically, it doesn't exist on this, between this carbon and this oxygen, or this carbon and this oxygen all the time. It's usually a mixture of both, right? So we share the electron density, and you get something that can look like this. This is like rapidly alternating between these two structures here. And so when you get that, you get this stabilization effect, which means that this molecule is okay with donating its proton. We say it's proton because all of the electrons from this proton stay with the oxygen. That's why it's left with a negative charge here. We don't take any electrons with us when this proton leaves. And that's, just a positive charge, a little proton floating around in solution is very, very reactive. So it's usually picked up by a water molecule that stabilizes it. And then that ends up creating our hydronium ion, which is H3O+. And it's the concentration of this that relates to the pH of a solution, right? So these are all part of the same structure. These acids usually have a proton that's bonded to an oxygen that makes it what we say acidic. It doesn't always come from protons that are bonded to oxygen. So this is an example of what we call an oxyacid because it's bonded that way. But another strong acid, for example, is hydrochloric acid, HCl, where that gets rid of its proton very fast too, and you just get chlorine ions in solution. And so these are always donating protons to their solution. Bases, on the other hand, we don't necessarily think of in terms of donating protons a lot of the time. They're usually something that's a source of hydroxide ions, but they can also be a source of hydroxide ions, not by donating it directly. So if we look at these three here, or these two here, these are ionic solids, right? So what we have is we have this hydroxide ion and sodium that are bonded to each other in an ionic bond. We put that in solution and it just gets rid of that OH minus, right? When it gets rid of that OH minus, that makes the solution basic. Whereas ammonia, on the other hand, is going to work slightly differently. This pulls protons from water. So this will do something like NH3 plus H2O, which is liquid water, will go to NH4 plus OH minus, right? So we still create the hydroxide ion that makes the solution basic, but it pulled one of the hydrogens from water, or it pulled the proton from water, right? Because it's not the whole hydrogen, it doesn't have the electron, and it does that and it creates this. So that's why ammonia acts basic in these cases. So bases, you know, they either donate OH minus directly or they create OH minus by some other method in solution. And so depending on the type of way it interacts, usually these acids and bases are classified different ways. So there's three main types of acids, right? So there's three types of acids and bases, and each one is usually consistent with each other, but sometimes they expand the definition of what an acid and a base is, right? So the Arrhenius acid and base is generally going to be the most simple. And then if we go to something like a Lewis acid and base, that can expand the definition of something that isn't necessarily an Arrhenius acid or base, but is a Lewis acid or base, and actually does make solutions acidic, right? So there's kind of these definitions kind of get more refined as we focus them a little bit. And so the Arrhenius definition is that substance that produce hydronium ions, H3O plus ions in solution, that's what we call an acid. And something that produces OH minus ions in aqueous solutions, that's what we call a base. And so this is something that directly produces that. However, we know there are other compounds that do make solutions acidic or basic, meaning that they do produce H3O plus ions or OH minus ions, but they don't do it directly by donating that to solution. Like hydrochloric acid gives its proton to water and creates H3O plus. Sodium hydroxide just creates an ion of hydroxide ions when the ionic compound dissociates. However, we know other things like boron compounds, aluminum compounds, highly charged metal cations, those can also act acidic, meaning they do change these concentrations in solution, but they don't do it directly by working with water. They do it in other ways. And so that's why we have multiple definitions for all of these. So if we think about something like hydrochloric acid, it's a strong acid, and so what it does is you put HCl, and it can be aqueous or not, in water, and we create H plus ions and Cl minus ions. The H plus ions, or protons, are usually picked up by the water molecule to then change the acidity or basicity of the solution. And so you'll see this a lot, especially dealing with acids and bases, that H plus concentration and H3O plus concentration are used interchangeably. Why? Because you're always assuming that this process is happening, right? This water molecule that has these lone pairs can then pick up this extra hydrogen, right? It picks up the extra hydrogen because the proton's attracted to those lone pairs. Again, if you think about it, this is like a single proton that's just floating around in solution. That's what acidity is defined as. And where does that proton go? Well, usually one of those surrounding water molecules picks it up. Now we have this ionic compound that's then dissolved in the water, right? So initially you have it's liquid water, but it becomes this aqueous ion that's then dissolved in the water. The concentration of that is going to be related to the acidity or basicity of the solution. And so similarly for bases, we can have a little bit more simpler process. We don't necessarily need to interact with water, because if we have sodium hydroxide, which is a solid or can be a solid, it doesn't have to be, this will just dissociate once we put it in water, because it's a strong electrolyte, into sodium ions and hydroxide ions. And because it made hydroxide ions, then it will be considered an Arrhenius base, right? All that matters for the Arrhenius definition is, do we create H3O plus, or do we create H3O plus, or do we create OH minus? And based on this definition, a neutralization process is one where acids and bases combine together to form water, right? So if we had sodium hydroxide, let's say it was aqueous, and we added it to hydrochloric acid, and now it's aqueous, what happens is, instead of changing the pH of the solution, so this is what you're doing when you're doing a titration, right? The hydroxide ion from the sodium hydroxide is going to combine with the proton from the hydrochloric acid to then create water. So we're going to have H2O, it's just liquid water, plus these will either stay as ions or you'll have some sodium chloride mixture, right? Usually you're not going to have sodium chloride because it's a strong electrolyte, but it could precipitate out of solution potentially as well, right? So you have the HCl plus NaOH. This proton combines with the OH minus that we created there to then make water. So this is what a neutralization process refers to. The Bronsted-Lowry definition, right, is going to expand what we think of acids a little bit, because it's not just about making H3O plus or OH minus in solution, but instead is looking at the transfer of protons in acid-base reactions. Since H plus is literally just a proton in solution, this definition focuses on the idea of proton donors and proton acceptors. So based off of what we talked about the structure of acids, right, when we talked about resonance and whatnot, and oxyacids a little bit ago, what do you think an acid is? Is it going to be a proton donor or a proton acceptor? It should be a donor, right, because it's usually getting rid of that proton, right? So acids are proton donors. Bases are proton acceptors. And so now that allows something like ammonia to then act in a neutralization process, right? So if we have HCl plus NH3, we can say ammonia acts like a base in this way because ammonia accepts the proton, it's a proton acceptor, and hydrochloric acid is the proton donor. So this becomes Cl minus plus NH4, right? So we're thinking about this in a neutralization process. We didn't create water necessarily here, but we add something acidic and we have a base there. And that base can now accept the proton. So this is considered a base in this reaction, right? So we don't necessarily have to create water in this neutralization process, right? Because now a base is not just defined as something that makes OH minus in solution, but something that accepts protons. And a lot of times if we just put ammonia in water, it's going to pull a proton from water. And that also creates OH minus in solution. And so, according to this definition, hydrochloric acid is an acid because it donates a proton to water. Right, so HCl is then going to go to H3O plus Cl minus, right? It donates the proton to the water molecule, right? Because water has the lone pairs and can pick up that proton. And then ammonia is considered a base in this context because it accepts a proton from water. It becomes NH4 plus, and then the water molecule is just left as a hydroxide ion. So in both of these cases, we still created H0 plus and OH minus like we do in the Arrhenius definition. Except we're not considering it an acid or a base because of that, we're considering it because it's donating or accepting the protons. And so that means for neutralization reactions, you can then identify what's going to be the acid and what's going to be the base. And so here we have these acid-base pairs, and we'll find that for Lewis acids and Bronsted-Lowry acids, you get what we call conjugate pairs. We want to ask ourselves which one's going to be the acid and which one's going to be the Bronsted-Lowry acid and which one's going to be that Bronsted-Lowry base, right? So which one is going to be the Bronsted-Lowry acid here? And then how do you know? Right, we have the original acid or base, we're always looking at the reactant side of the equation, right? So we're deciding between these two. Which one is going to be the acid and which one's going to be the base, according to our definition of a Bronsted-Lowry acid or base. Arhelia? Yep, it's our acid, and why is it our acid? It donates the proton, right? So on the right hand side, on the product side, we see it's lost its proton at this point. The C2H5 is then going to be our base because it has accepted the proton in this case, right? So here we accepted the proton, and here we lost the proton. Right? So this means that this was the donor and this was the acceptor molecule. And just to preface what we'll talk about more, that's the acid. We call this the conjugate base. We call this the conjugate acid of the base. Why? Because if we flip this reaction around, now they act opposite to what we just said that they did. Okay, what about in this reaction here, right? So now we have water in this reaction, which we generally don't think of as an acid or a base. But water is actually going to be one of the compounds that can act as both an acid or a base. And how do we determine that? Well, in the Bronsted-Lowry definition, it's by the movement of protons, right? So this reaction is moving in a certain direction. Which one's going to be the acid and which one's going to be the base? The water is going to be the acid because it's donating a proton, right? This is the acid. And then the chlorine ion is going to be the base. Why? Because it accepts the proton, right? It's the acceptor. And then the acid is the donor of the proton, right? In this one, probably not very likely to see in real life because hydrochloric acid is a strong acid, meaning it dissociates 100% solution. There's a finite, a very, very small compared to the concentration of everything else, amount that this is actually going on. But based off the reaction you're given, that's how you would define these two molecules. This is acting as the base here, or the acid, the water is, and the chlorine ion is acting as the base. And so according to these definitions I mentioned, you get something called conjugate acid-base pairs. All right, so these are conjugate pairs. Right, so one on the reactant side of the reaction, we have either our acid or base. And then the other side, when it donates or accepts a proton, what you're left with is called the conjugate pair for that. So if you start off with an acid, it'll end up as a conjugate base after it donates a proton. If you start off with a base, after it accepts the proton, it becomes a conjugate acid. And so some compounds, and we use this idea to kind of define equilibrium for acids and bases, they can act as both acids or bases because they can both accept and donate protons. These substances are called amphoteric compounds, right? So water is one of these things, right? Because we already seen an example where it donates a proton and where it accepts a proton. And so if we look at this first reaction, we see that hydrochloric acid here is the acid, water is the base because it accepts a proton, which means that the hydronium is the conjugate acid in this case, and then the Cl minus ion is the conjugate base. The conjugate base comes from the original acid, and the conjugate acid comes from the original base. All right, so this depends on the direction of the reaction that we're looking at. And the same way in the bottom, we have the ammonia acts as the base, the water acts as an acid. So we see now water is acting as a base in the first reaction and acid in the second. And so OH minus is going to be the conjugate base. And then ammonia is going to be the conjugate acid. And so I mentioned that this depends on the direction of the reaction, right? So if we reverse this reaction, then now one is acting as the acid, the other one's acting as a base, which is why we use conjugate base pairs. So the conjugate pairs depend on the direction of the reaction. Right, so if this is going forward, ammonia is acting like the base because it's accepting the proton. However, if this is going in the reverse direction, ammonium is acting like the acid because it's donating a proton to the OH minus. But if we identify the pair, then it would just be the opposite of what pair, right? So ammonia is the base originally, NH4 is the conjugate acid. But if we flip it around, NH4 is the acid, and the ammonia is the conjugate base of that because we've donated the proton. All right, so sometimes it's easy to look at the charges independent to see how that happened, but really the movement of the protons is a more accurate way to look at how things change, right? Because we can have a conjugate base that isn't charged, that isn't negatively charged, like in the case of ammonia. Okay, and I already talked about that a good amount. Let's see, okay, all right, so we'll leave it there for today because we don't have maybe a minute left. And we'll start talking about Lewis acids and bases next time because that expands our definition even more. And then we'll start talking about principles of equilibrium and how we use them to understand acids and bases.